Welcome to today's Explainer. If you've been keeping an eye on the tech world lately, you've probably noticed there is a massive, literal hardware race happening right now to build the ultimate quantum computer. We are way past the theoretical stage at this point. Companies are actually sprinting to build the physical machines that are going to define the foundations of our future internet, medicine, and AI. But how exactly are they doing it? And maybe more importantly, whose hardware is actually going to win?
Okay, let's dive right into our race card for today so we know exactly who we're looking at. We're going to cover the core scaling problem, then silicon spins without microwaves, IBM's hybrid gamble, the quantum dot bus, room temperature diamond qubits, and finally, the race to scale.
Section 1. The scaling problem.
Right now, the quantum industry is hitting a massive bottleneck. And ironically, it's not a lack of options. We actually have a surplus of options for the basic building block, the qubit. Just as a quick refresher, a qubit is simply any quantum system that can alternate between two well-separated energy states. If you can trap it and measure it, you can probably use it. So today we've got engineers building qubits out of atoms, ions, photons, and manufactured devices holding just a single electron. But here's the thing. The true winner of this hardware race won't just be whoever makes a working quantum system, it's absolutely going to be the one who can scale that system to handle incredibly complex computations.
Because to do any actual useful computing in the real world, we are going to need thousands upon thousands of these high-quality qubits. So the million-dollar question is, how on earth do we get thousands of these incredibly fragile, microscopic systems to work together without everything just completely falling apart? Well, that brings us to our first technological competitor attempting to solve this exact scaling nightmare.
Section 2. Silicon spins without microwaves.
Enter our first competitor, HRL Laboratories. Their approach is really fascinating. They use manufactured quantum dots that rely on electromagnetic interactions to trap a single electron in a tiny patch of silicon, and then they use that electron's spin as their qubit. Now, typically, keeping those electron spins stable is incredibly hard, and you have to control them using microwave pulses. That means you need separate control systems and a massive amount of bulky, microwave-carrying cabling feeding into a refrigeration system that is kept near absolute zero. But HRL, they completely threw that rulebook out. They're using 3 separate quantum dots and controlling the interactions of those 3 electron spins entirely through standard electronic wiring. Literally 0 microwaves needed.
And because they ditched the microwaves, HRL managed to create a control system that sits at an intermediate level of refrigeration. It's totally separate from the absolute 0 qubits, connected only by a simple superconducting ribbon cable. And the power draw on their custom 130-nanometer controller, an astonishingly low 3.5 watts. It's this completely autonomous, low-temperature, low-power marvel.
Now you might be asking, is this a massive system yet? Well, no. HRL's system currently sits at 18 qubits, but when they ran a simple error correction code on it, they demonstrated a logical error rate of less than 1%. That is incredibly low, and honestly, it's a massive validation. It proves that the hurdles standing in the way of scaling this specific silicon wiring approach are just engineering problems. They aren't fundamental physics problems anymore.
Which leads us to Section 3. IBM's hybrid hardware gamble.
You see, the progress HRL made was so undeniably appealing that IBM actually went ahead and bought the company. And this was a huge shock to the quantum business world. Why? Because historically, IBM has bet almost entirely on a completely different technology, a manufactured device called a transmon. And transmons are controlled by the exact same microwave pulses that HRL just proved you don't actually need. But IBM's director of research, Jay Gabetta, explained the strategy behind this shock acquisition. He said, "I'm a strong believer in silicon technology. It gives us flexibility to keep both parts going in parallel, build on the same foundation. Basically, both superconducting transmons and these new spin qubits are built on silicon. By owning both, IBM is betting big on a hybrid future." Gabetta noted that as we look at error correction codes going forward, some might be better at acting as memories, like the transmons, while others, like HRL's tech, might be better at magic state creation, which is essentially prepping the system for complex, error-free calculations. IBM just wants the flexibility to build hardware that maximizes the absolute best of both worlds.
Section 4. The quantum dot bus. So, standard manufactured qubits have a pretty major flaw. They are completely stuck where you place them. You are 100% committed to the rigid geometry of that single chip's wiring. But a brilliant team over at Delft University of Technology asked a crazy question. What if the qubits could move? They created a system that works exactly like a microscopic transit system. An individual electron spin waits in a quantum dot. Think of it like a bus stop. Then, when it's needed, it actually moves along a 1.2 micrometer bus route across the chip, passing through intervening dots until it arrives at an empty dot right next to another electron. Boom! Arbitrary entanglement. Any two spins can be brought together.
And this brilliantly illustrates just how effective this movement is. Delft achieved nearly a 98% fidelity when sending a spin from one end of this microscopic bus to another and then back again. By allowing these qubits to move around arbitrarily, they are essentially combining the highly reliable manufacturing of silicon chips with the ultimate algorithmic flexibility of atom-based systems. It's a real game changer.
Now, to be fair, it isn't perfect just yet. While they were implementing a small error correction code, the Delft researchers were super transparent about their current hurdles. Mostly, they're fighting noise that pops up during the actual spin exchanges required for entanglement, alongside a loss of coherence while the qubits are either moving down the bus or just idling at a stop. It's definitely a common problem with spin qubits, but it's one they will systematically have to solve if they want to scale up.
Moving on to Section 5, Room Temperature Diamond Qubits.
Okay, about a decade ago, using nitrogen vacancies in diamonds was a really hot topic, and then it suddenly just went quiet. To give you some context, diamonds are basically just regular arrays of carbon atoms. But if a nitrogen impurity gets in there, it forms one less bond than carbon does, which leaves a single, unbonded electron. And you can manipulate the spin of that lone electron exactly like a quantum dot. The historical problem with diamond qubits, though, was that we couldn't control where those nitrogen impurities ended up. Every single chip was a bespoke, random mess. But Q, which is a spin-out from University Leipzig, just cracked the code. They developed a technique that can accurately place these nitrogen vacancies within a microscopic 10-nanometer radius. To put that into perspective, that's roughly the width of a single cell membrane. It is insanely precise.
And because they solved that precise placement issue, we get this. It runs perfectly at room temperature. No joke. No massive absolute zero freezers that look like giant sci-fi chandeliers. No massive cooling tubes. Q's machines fit right into a standard rack mount and literally plug into a normal power supply. This is the absolute holy grail of quantum hardware deployment.
So the crucial point here is rapid scaling. Because they don't need giant freezers, Q is able to build a modular 8-qubit core design. You just stack them. They're already selling standard rack units with over 100 qubits total, and they're expecting to ship within months, with even larger systems coming next year. And the individual hardware qubits, they're hitting a gate fidelity, which is the reliability of its operations, of over 99.9%. This room temperature tech is highly, highly competitive.
And finally, Section 6, the race to scale.
Let's bring this all together and see how this builds. All three of these technologies are absolute marvels of modern physics, and they're all sprinting toward the exact same finish line, scaling up to thousands of high-quality qubits to perform complex, error-corrected computations. Think about it. HRL gave us silicon spins with less than a 1% error rate to finally ditch those bulky microwaves. Delft gave us the dot bus for completely arbitrary entanglement across a chip. And Q delivered diamond defects that can actually run in room temperature servers.
It is just a thrilling time to watch this space. The foundational engineering barriers that held us back for years are falling one by one. But it leaves us with the ultimate question as we watch this incredible hardware race unfold. Which of these architectures will be the definitive one that finally allows quantum computers to scale? Will it be silicon spins, microscopic moving buses, or room temperature diamonds? Or actually, could it be some sort of hybrid of them all? Keep your eyes on this industry because the very foundation of tomorrow's computing is literally being built right now. Thanks so much for joining me on this explainer, and keep learning.